Okay, in section 2.2, we're going to talk about more about functions and their graphs. More on functions and their graphs. So it really is just kind of a continuation of 2.1. All right. So one of the first concepts we're going to talk about is this whole idea about increasing, decreasing, and constant. Increasing, decreasing, and constant. So hopefully the idea of something increasing or going up or getting bigger makes sense, at least from a non-mathematical standpoint. But that's the idea. Something which is increasing is getting bigger. Now, for mathematics, there is a much more difficult definition mathematically. It's very symbolic. But if you just understand that it's getting bigger, and um, the biggest thing is when you read a graph, you read the graph from left to right. Okay, we don't ever read the graph backwards. So you read it just like you would read a book. You read left to right. Something which is getting bigger from left to right is increasing. Likewise, something which is decreasing would be getting smaller or going down. And again, left to right. Constant should make sense. It's neither increasing nor decreasing, therefore it is not changing. Again, from left to right. Now, the one thing we're going to say about constant is this. Constant indicates more than one value. Because there are going to be times on a graph where something does not increase nor decrease at a specific point, but at one point we don't call it constant. It has to be at more than one point, more than one consecutive point, that something is not changing from left to right. So let's go ahead and take a quick graphical look at what this would be. And this is just a really simple sketch. So if we have some kind of a graph, whatever it looks like, and it does this. Well, from left to right, and I apologize for the little squiggles, that's actually something that's going on with the screen. That has nothing to do with the way I'm drawing it. From here over to here, this thing is going up. Okay, you should be able to see it's constantly moving up. Again, left to right, it's moving up. Sometimes it's moving up quickly, sometimes it's moving up slower, but it is moving up, so this is increasing. Likewise, something that might look like this is moving down constantly from left to right. You can kind of see the direction of those arrows. It is indicating it's moving down, so that's decreasing. And then something which is not changing, it's not increasing or decreasing, would be something that looks like this. It's just a horizontal line of some kind. And that is constant. Not increasing, not decreasing. All right, so let's go ahead and look at some examples. What we want to be able to do is we want to be able to look at these graphs and we want to figure out what intervals things are increasing on, what intervals things are decreasing on. So we're going to go back to our interval notation. And what we should see is if I follow this graph, this letter A, I'm going to put this in red. If I follow this, now this arrow indicates it keeps going up, so it's going to go up forever to the left, but we read a graph from left to the right, so really it's coming down this way, all the way up until I hit right there. The function is decreasing all the way up until I hit there, and then you should be able to see it turns around and goes back up. Well, all the way to the left, the furthest that I can go that way, this function is going up and to the left as far as we want it to go. which means it's going to start at negative infinity. So this thing is going to be decreasing from negative infinity all the way up to the next, and this is going to be a set of x values, so it's just following your x values, all the way up till x is 0. Now at 0 itself, the function is neither increasing nor decreasing because it's actually changing directions. So we don't include the 0. It's an open interval. Well, if you look closely at the graph, there's actually some other places on the graph where this thing is going down. It starts right here and then comes down forever down and to the right. So it looks like it's going from x equals 2. So this is a union with x equals 2, and then again all the way forever into infinity. There is only one small section of this graph where the function is increasing, where it's going up. And again, I think graphically you can see this. It's just going to be writing the intervals that might take some time. But you should be able to see that from here to here, all the way up along this line, the graph is going up. And that's going to go from x equals 0 to x equals 2. So from 0 to 2, the graph is increasing. All right, hopefully that makes sense. Let's look at B. So we're going to want the same things. And by the way, in letter A, there was no place that this thing is constant. There's no place that you have a horizontal line anywhere. In letter B, let's look at where this function is decreasing. Well, if I look from left to right, looks like it's not decreasing, not decreasing, not decreasing. It doesn't look like it's decreasing anywhere. It's either constant or it's going up. So in this case, there are no nor none for the intervals of decreasing. Increasing, I can definitely see that the graph does have an increasing portion. It is going up from left to right. And it looks like it's going up from left to right from here all the way up this way, and it's going to go on forever. So really it's going to keep on going forever in the x and the y direction to the right. But there's an open circle on 0. Doesn't change anything. It's still basically starting at 0, but since you don't include the 0, you still put the open parentheses anyway. And it's increasing all the way up to infinity. The only time that we're actually going to include the constant, so we'll put this in, we'll do this in blue, I guess. The only time we're going to include the value is if you have something which is constant. In this case, we do. You should be able to see you've got a horizontal line, which means that it's not going up or down for values which come from all the way to the left, all the way up to, and including, because there's a closed circle there, 0. So it means it's going to be constant from negative infinity all the way up to, and this time, including the 0, because it is still constant at 0. If it was increasing or decreasing and those two things met, then you would actually not put the solid bracket. But because it's constant, we can actually put the solid bracket there. All right. Again, hopefully that makes sense graphically. Hopefully you can visually see that. Just make sure you get the intervals correct. Remember, you're dealing with x values when we're talking about the intervals of increasing and decreasing. Now, along with this, and you can probably see it on this first graph, we'll do another one just to make sure. You have what are called relative maximum and minimum values. Maximum and minimum should make sense. Maximum is a highest value. Minimum is a lowest value. Well, if you look at this first graph, I'm going to redraw it, technically goes on forever. So is there really a highest and is there really a lowest value on the entire graph? No, because it goes up to the left forever and it goes down to the right forever. So there's no highest and lowest value on the graph. But within a local region, there is. And this is why we call it a local maximum or a local or a relative minimum. Because within a small region, there is. I have a localized minimum. If I just kind of partition this off, in this general region right here, let me highlight this, see if this works. In this region, nope, that didn't work. Nope, highlighter's just not working for some reason. Oh well, I tried. But right around 0, where I put those parentheses, you can see that there is a minimum value at the bottom of this hill. Um, and that minimum value is the y value. That minimum value there would be 0. We're not going to write it for this one. We're going to do a different one. You can also see that there's a local maximum right here. There's a top of a hill right there. That's what's called a local or a relative maximum. And that y value looks like it's about, what, 4? So when we ask for maximum and minimum values, we're asking for y values. What's the y value? That is what a maximum or a minimum of a function is. So I think I've got some another graph on this on the next page here. Let's see. I do. So we're going to look at this graph, and we're going to try and determine from this graph what the maximum and minimum is. We're going to try and figure out what the intervals of increasing and decreasing are, and then we'll go from there. So let's talk about the intervals of increasing and decreasing. So it looks like this one is increasing all the way up till I get to right there, which looks like it's at about -1. So we're increasing from negative infinity to -1. It also looks like it's increasing from 1 and then forever off to the right. So that's going to be in union with 1 to infinity. The function looks like it's decreasing in between those. What it looks like between -1 and +1, the function is decreasing. And then let's talk about the local or the relative max and min. So the way we do that is we put relative max, relative min. Now we're not talking about a point. When they ask for the max or the min, we're asking for the y values. Max or min is the y value. If you give me the x value, you're just giving me the location of the max or the min, but not the actual maximum or minimum value of the function. So we're going to have to do some estimation here because this one doesn't work out nicely on the graph. But it looks like right here is the top of a hill. Kind of missed. Let me try that again. Right here is the top of a hill. And it looks like that's someplace right in between 0 and 5, so we can estimate this to be about 2.5. It looks like the relative maximum is about 2.5. And then it looks like we have a relative minimum at the bottom of this little hill, right there. And it looks like, again, it's in between the 0 and -5, so we'll call it -2.5. Usually if we're asking for the max and min, it's going to be a little bit easier to figure out graphically like that. Okay, and there was no intervals of constant on this thing because there was nothing where it was completely horizontal. All right. Let me see what's on the next page here. Okay, we're getting ready to get to that. Okay, there are 3 types of symmetry that we can have. What I will tell you is that the vast majority of graphs are not symmetric at all. But when you do have symmetry, it's good and it's useful to be able to figure out what they are. 3 types of symmetry. Actually, there's multiple, but there's only 3 we're going to deal with right now. There's more than just 3. You can have symmetric. Actually, I'm not going to keep writing symmetric. Symmetry to the y-axis. Symmetry to the x-axis, and symmetry to the origin. Okay, something which is symmetric to the y-axis means that basically if you took your graph and you folded it over the y-axis, literally created a fold on the y-axis, whatever the graph looks like on the left would be exactly the same as what it looks like on the right. Let me show you on this next page what that is. So the first one here, if I took and I folded this graph right over the y-axis, hopefully you can visually see that this piece would lie right on top of this piece. They would be identical. That's what it means to be symmetric to the y-axis. Okay, and the second one, if I took and folded it right over the x-axis, again, you should be able to see that this piece right here would lie right on top of that piece. So that would be symmetric to the x-axis. And then the one that's a little bit more challenging to do, hopefully you can see it, but how do you fold something over the origin? Well, you really don't. Technically, you could fold this one in a different way. It's actually symmetric to something else, but folding it over the origin isn't exactly what we're trying to do. What symmetric to the origin is, because this is the last one, it means if I took this graph right here, which looks like this, and looks like this, and I rotated the whole graph. I wish I could do this for you guys, but I can't actually take this whole thing and rotate it. If I rotated this graph 180 degrees, so if I rotated it 180 degrees, basically it's taking the graph and turning it upside down. So if you have this drawn on a piece of paper, take your piece of paper, turn it upside down, it should look identical. What's happening is it is revolving around the origin, so it's taking this piece and moving it down to here and taking this piece and moving it up to there. It's 180 degree rotation around the origin. Another way to think of it is if you put a pencil right through the origin and then you started to turn the paper 180 degrees or upside down, it would look identical. That is symmetric to the origin. The blue one and the red one have specific meanings to stuff that we're going to do later. The green one, it's if you have something which is symmetric to the x-axis, it's not really a function, so it's not going to help us a whole heck of a lot for what we're doing. So what we want to do is we want to be able to test for symmetry and see if something is symmetric. And we want to be able to do it, so visually you should be able to look at something and kind of tell whether it's symmetric to the y-axis, x-axis, origin, or just none of these, which is quite possible. But we want to be able to do it algebraically. So we want to be able to test for symmetry. So if we have the graph x equals y squared minus 1, if you happen to know what this graph looks like, it's really easy to tell what's going on. That's not going to be the easiest thing to do for most people. So this is what you get. This is what you're going to do. If you want to test to see if this thing is symmetric to the y-axis, so this is your y-axis test. If something is symmetric to the y-axis, you're going to replace x with negative x. And then you're going to simplify it. If you get exactly the same thing that you started with, the original equation, then it's symmetric to the y-axis. So let's do a test. I'm going to replace the x right here with negative x. Okay, are these two things equal? No, definitely not. Y squared plus 1 is the same, but the negative x is different than the positive x in the top one. So this is not symmetric to the y-axis. Let's test to see whether it is symmetric to the x-axis. Okay, if we want to test x-axis symmetry, instead of replacing the x with negative x, now we're going to replace y with negative y. I'll show you why this is in a second, so I'm not just telling you what to do. Okay, so let's try that. If I replace the y, replacing that right there with a negative y, I get x equals, plug in the negative y, square it, minus 1. Well, negative y squared, negative y times negative y is y squared minus 1. These two things are the same, which means this graph is symmetric to the x-axis. All right. If you wanted to test symmetry to the origin, you would replace all of the x's with negative x, all the y's with negative y. So replace x with negative x and y with negative y. And then again, if you do that and you get the exact same thing that you started with, then it'll be symmetric to the origin. So we'll go back up. I'm going to place x with negative x, so that'll give me negative x equals, replacing y with negative y will give us negative y squared, and I think it was a plus 1, plus 1. Simplifying that, I get negative x equals y squared plus 1. This is not the same. So it is not symmetric to the origin because that's not exactly what we started with. So those are your three tests. Now let me go back up to this graph real quick, and I'm going to show you why these tests work. Look at the points that they gave us. If I look at the first graph, which is symmetric to the y-axis, if I take any x value, like let's just say that x is 2, whatever it is, and I go out to the 2 and then up to the graph, that graph is going to be right there, so we'll say that that's 2. If I were to go to x is negative 2, it's the same distance away, but on the left, look what happens to the y value. It should be in the identical place. It doesn't make any difference if I plug in a positive x or a negative x, it should spit out the same y value. That is something which is symmetric to the y-axis. So you can replace x with negative x and you should get the same thing if it's symmetric to the y-axis. Likewise, on the second one, which is symmetric to the x-axis, if I go to some y value, we don't usually do it this way, but if we go to some y value like y is 2, and I go to the graph, well, that gives me a specific x value, whatever that is. If I go to y is negative 2 on the graph, and I go over here, it should spit out the same x value. So if I replace the y value with a negative y value, it should give me the same x value. Therefore, it would be symmetric to the x-axis. And then over here, on the symmetric to the origin, if I give a positive x and a positive y, for it to be symmetric to the origin, that would have to be that if I put in negative x, so here's positive x, positive y, if I put in the negative of that x and the negative y, it should, I didn't place that very well, but it should give me the same point symmetric to the origin. All right, not as easy to understand with the origin one, but the first two hopefully should make a little bit of sense. And that's your symmetry testing. So the blue and the red, like I said, have special meanings. If something is symmetric, there we go. If something is symmetric to the y-axis, it is what is called an even function. I'm not actually sure where that came from, but that's what it's called. It's called an even function. So it's just a special name for being symmetric to the y-axis. If something is symmetric to the origin, it is called an odd function. Notice we don't put anything for the one for the x-axis, because if it is symmetric to the x-axis, as we learned in the previous section, it would fail the vertical line test, therefore it would not be a function at all. So there is no specific type of function that you would associate with something which is symmetric to the x-axis. It would not actually be a function at all. So the algebraic way of saying something which is even, if it is even, the following will be true. F of x will equal f of negative x. Because again, remember, it doesn't matter if I plug in a positive or a negative of x, it should spit out the same y value. Algebraically, if something is odd, this is a little bit different because we don't use x's and y's here. What this says is that f of negative x is equal to the negative of f of positive x. Now, if you can really see this, then you're doing okay. If not, you might just want to kind of memorize the formula. But if you kind of just look at the left, this f of negative x, that really means I plug in a negative x value and I get out a positive y value. So that's a negative x and a positive y. That says these should be the opposite because it should be symmetric to the origin. Well, that says I plug in a positive x and I get out a negative y. So they really are opposites. So that's what that's trying to say there. If that makes sense to you, that's wonderful. If that doesn't make sense, you might just kind of want to memorize these formulas. So let's go ahead and see if we can identify whether a function is odd or even or neither, because that, again, happens quite frequently. All right. So let's have the function f of x equals x cubed minus 6x. We want to test to see whether this is an odd function, even function, or neither. If it's an even function, f of x would have to equal f of negative x. So what I need to evaluate is f of negative x. And if you recall from the previous sections, that just means I'm going to take negative x and I'm going to plug it in where x was in these equations. So I'm going to have a parentheses cubed minus 6 times a parentheses. I'm going to substitute negative x in there. And then we'll simplify and see if this is exactly the same thing as what we started with. So simplifying, negative x cubed is negative x times negative x times negative x. That actually gives you negative x cubed. Here, negative 6 times negative x is positive 6x. This is not the same as what we started with. So this is not even. So now we need to test for odd. The good thing is, an odd test starts with what we just found. It's f of negative x has to equal the negative of f of x. So I'm going to see if this guy right here is the same as negative f of x. Well, the negative f of x really is just taking the entire function that we started with and making it negative. This is the entire function, so I'm going to make the whole thing negative. So negative f of x is the negative of all of this. Well, we just distribute the negative through and see what we get. So that'll be negative x cubed plus 6x. Well, if you look, this is the same as this, which means that this is an odd function. All right. Let's go through another example. So we'll say that g of x is x to the fourth minus 2x squared. So let's test for even first. It's always the first one I do. So f of x would have to equal f of negative x. So or g of x in this case. So g of negative x, again, is replacing the x's with negative x. So let's put in the parentheses a negative x, and then simplify. Excuse me, negative x to the fourth power is negative x times negative x times negative x times negative x, which should give you a positive x to the fourth. Remember to do your simplification first. This negative x squared becomes positive x squared times negative 2 is negative 2x squared. These are the same, which means that this is an even function. And what I will tell you is this. If you get an even function, you don't even have to continue because it won't be odd. If you get an odd function, it won't be even. There is only one function that actually exists that is odd and even at the same time. I won't tell you what that is, but if you can figure it out, I should probably give bonus points or something like that. Anyway, there is only one that exists for. All right, let's do one more, and then we'll stop this video and we'll come back with a second video. So we'll do h of x. I apologize for the squiggly lines. This is something that has to do with the projector that I'm using. It doesn't have anything to do with my writing. I write bad, but not that bad. X squared plus 2x plus 1. Again, test for even first. F of x equals f of negative x. So in this case, we got to test for h of negative x. So we'll replace the x's with a negative x and simplify. So that'll be negative x here, negative x there. Negative x squared is x squared. 2 times negative x is negative 2x, and then plus 1 is still plus 1. These are almost the same, but not quite. The sign here and the sign here are different, so this is not even. Okay, let's see if it's odd. Odd means you would have to do the f of negative x equals the negative of f of x. So I need to find the negative, in this case, of h of x, which is taking the entire top function and making it negative. So we'll distribute the negative through and see what we get. Negative x squared minus 2x minus 1. Well, this definitely is not the same. These are not the same. So this is not odd, which just means this is neither. This function is neither odd or even. And again, that's probably the most common, but when we do get odd and even functions, they're helpful to be able to do. All right, I think we're going to stop this video, and we will come back with a second video, and that will have to do with piecewise functions and this thing which is called the difference quotient, and that'll actually finish it off. But those two things can take a few minutes.